Okay, so welcome back to this next video in which we are discussing the definition of a vector space. Okay, so we're currently trying to construct the vector space Fn over a field capital F, which is an arbitrary field. Okay, and we are at the moment checking that the addition law that I have defined on this set actually obeys the axioms of an abelian group. Okay, so we've checked closure, we've checked associativity, we've checked that we have a zero vector. What we now need to check is that we have inverse elements, additive inverse elements. Okay, so what we need to do is take an arbitrary vector, okay, from our set, and an arbitrary vector will be something of the form x1, x2, all the way up to xn. So here is an arbitrary vector, and what I now want to prove is that this has another vector. Okay, so this set Fn has another vector which, if I add it to this vector, will give me the zero vector, will give me the additive identity in my vector space. Okay, so quite simply what I'm going to do to find the additive inverse to this vector is I'm just going to take all of these components and I'm going to take their additive inverses in the field. Okay, so I'm going to find the vector of this form, negative x1, negative x2, all the way up to negative xn, where the negative of an element in the field is just the additive inverse of that element in the field. And because the field is an abelian group, all of the elements in that field, under addition I should say, it's an abelian group under addition, all of the elements in that field must have additive inverses. Okay, so for all of the components of the vector then, I can find their additive inverses in the field, and I claim that what I have here, which I will call negative v, is going to be the additive inverse of my vector v here in the vector space. Okay, so quite simply to see this, let's just add these two together and see that we get the identity back again, the zero vector. Okay, so we'll take v plus negative v, and the way of course that we'll do that, is component wise. So we'll add together all the components, so we'll take x1 here, okay, and we'll add that to negative x1, so we'll go plus negative x1, and then we'll take x2 and we'll end up adding that to negative x2, okay, and then we'll continue on all the way up to xn, which will add to negative xn here. Okay, and that will now be our overall answer. And of course what we can do is when we add all of these components to their additive inverses in the field, we'll just get the additive identity of the field. So in every single slot then, we'll get the additive identity of the field 0, 0, all the way up to the nth 0 here, i.e. we will get the identity vector back. Okay, and I hope you agree that if I did it the other way around, so if I did negative v plus v, okay, so I add them together the other way around, it will also give me the zero vector, the additive identity in my vector space. Okay, and that's because I can add together each of these components either way round, and if they're at each other's additive inverses in the field, they will give the additive identity in the field always. So indeed, I will just get this list of zeros as my answer, i.e. the zero vector. Okay, right. So there we have now checked that this set with the addition on it obeys the inverse criterion. And there's one final criterion that we need to check in order to check that under addition this set of symbols is actually going to form an abelian group. Okay, and that's commutativity. Okay, so we need to check that if I have two vectors v and v bar and I add them together, it's the same as if I do it the other way around, v bar plus v. Okay, and of course this is going to be true because of commutativity of addition in the field. Okay, so let's just take my two vectors, and as always I'll use the same notation. Okay, so on this side, v plus v bar will give us as the answer x1 plus x1 bar. Okay, and then the second component will be x2 plus x2 bar, and then it will go all the way up to xn plus xn bar. Okay, as my final nth component, whereas if I do it the other way round, I'll get all of these additions in the field the other way round. So the answer on the right hand side here that I'll get will be x1 bar plus x1 as the first component, x2 bar plus x2 as the second component, and then it will go all the way on till we have xn bar plus xn as the nth component here. Okay, so these are obviously going to be exactly the same because of commutativity of addition commutativity of addition in the field. Okay, so all of these answers here are going to be exactly equal to the answers here because of commutativity of addition in the field. Okay, so these two are indeed going to be equal to one another, so you can add two vectors either way around and you'll get the same answer. So this set of symbols, which is the set of all n tuples of elements of the field, with this addition law that I've defined, which is the most obvious addition law that you could possibly come up with, where you just add the components up in the field, this actually does form an abelian group. Okay, excellent. So now what we want to do is define scalar multiplication on this and hope that it's then going to obey the axioms that scalar multiplication needs to obey in order to actually be a vector space, and then we will indeed have a vector space over the field F. So I'll just get a new piece of paper to start this off with. Okay, right. So what I now need to do then is define scalar multiplication. So I need to define if C is an element of my field, capital F. Okay, so I've got some arbitrary element of the field, which I'll call C, and then I've got some arbitrary vector V, which is an element of Fn. I need to define what that element of the field C multiplied by the vector V is actually going to be equal to. So I need to define scalar multiplication. Okay, so the way I'm going to do this is I'm just going to do it component-wise. So now I'll write out what the vector is actually equal to. So it's this n tuple of elements from the field. So x1, x2, all the way up to xn here. Okay, and the way I'm going to define C times this is I'm just going to multiply all of these components on the left by C. So I'll get cx1 here, cx2 as the second component, and then it will go all the way up to cxn. Again, a very intuitive way of defining scalar multiplication in my vector space. Okay, now all I need to do is prove that if we have this definition for scalar multiplication of any element of the field with any vector in Fn, that it actually is going to obey those axioms that scalar multiplication needed to obey. So we'll start with axiom number 1. Now axiom number 1 was the easy one, remember. Axiom number 1 just said that for all C is an element of the field and all vectors is an element of the vector space, it must be the case that C times V is an element of the vector space, which in this case is Fn. Okay, so this just says that whenever you do multiply a vector by some element of the field, you must get another vector back again. Now of course that's going to be the case because look what I've got here. Okay, all I'm doing is multiplying all of the components of the vector by this element C, which is in the field, and this multiplication here is done in the field. Now when I multiply two elements of the field together, I get another element of the field. So in position 1 I've got an element of the field, in position 2 I've got an element of the field, and so on all the way up to position n. So indeed this answer that I get here will be an element of Fn. Okay, so closure is a nice easy one here. Okay, it follows straight from the definition. Next up, axiom number 2, associativity. So we need to prove that whatever two elements of the field you pick, C1 and C2, which are from the field capital F, okay, and whatever vector you pick from the vector space Fn, okay, we need to prove that C1 of C2 V is equal to C1 multiplied by C2 in the field times V. Okay, so this is our axiom number 2. So we need to prove that scalar multiplication associates or is associative with the multiplication in the field. Okay, right, and this really links the vector space and the field up now. Okay, so let's just apply the definition then of scalar multiplication that I've come up with to both sides here and show that what I get overall will be the same answer. So firstly, let's do the left-hand side here. So what I'm going to do is I'm going to just firstly write in my vector here. So we're doing C1 of C2 times my vector, which I'll call x1, x2, all the way up to xn here. Okay, now if I want to do that, firstly then let's do C2 times my vector here. Now when I do C2 times my vector, I'll just multiply all of the components by C2, so I'll just move this up. So I'll do C2 times x1, then I'll do C2 times x2, and we'll go all the way up until we get C2 times xn there, so that's the answer to this inner bit. And now what I want to do is multiply that by C1, and again what I'll do is just multiply all the components by C1. So the answer that I'll overall get then, and I'll put it underneath here, will be C1 times C2 times x1 here as my first component. Then I'll have C1 times C2 times x2 as my second component, and it will continue on up until C1 times Cn times xn here. Again, the brackets are important because I'm firstly multiplying C2 by each of the components here, okay, and then I'm multiplying C1 after that. Okay, so this is the answer that I get if I take the left-hand side here. Okay, now what we need to do is use the definition to the right-hand side here and show that the vector that I end up with is going to be the same. So what I'm going to do is I'm going to multiply C1 times C2 in the field by the vector, x1, x2, all the way up to xn. Okay, so the way that I'll do this is I'm just going to multiply C1 times C2, which is some answer in the field here. Okay, this is just some element of the field. I'm going to multiply that by each element of the vector, each component of the vector. Okay, right. So the answer then that I'll overall get will look like this. We'll have C1 times C2 times x1. Then we'll have C1 times C2 times x2 as my second component, and it will go on and on all the way up until you get to C1 times C2 times xn as my nth component. So that is the answer to the right-hand side of this equation. Now obviously these two things are indeed going to be equal to one another because all of these multiplications here, these are all just multiplications in the field. Okay, and multiplication in the field is associative, so this thing, for instance, just to take one example, here, this, C1 times C2 times x1, will equal this, okay, and that will be true for all of these components. So indeed, these two things are indeed going to be equal to one another with my definition of scalar multiplication. Okay, so that went well. Now let's do axiom number 3, which concerns the identity element of the field, the multiplicative identity specifically. Okay, so we want to show that the multiplicative identity of the field will multiply by any vector to give v back again. Okay, now again, this is a nice, easy property to understand. Okay, all we need to do is just put in my arbitrary vector now. So we're doing 1 times my vector, which will look like this, x1, x2, all the way up to xn here, and of course the way that I'll do this is I'll just multiply all of these components by 1 in the field, so it'll just be 1 times x1, 1 times x2, all the way up to 1 times xn, and of course when you multiply any element of the field by 1, the multiplicative identity, it has absolutely no effect whatsoever, so the answer that we'll get here will just be all of the components unchanged. So the answer here is just x1, x2, all the way up to xn, so it hasn't changed the vector at all. 1 multiplied by any vector is just going to give that vector back again. So indeed, axiom number 3 is satisfied. Okay, now axiom number 4, the two distributivities. Okay, so we'll have axiom number 4 part 1 first. Okay, so axiom number 4 part 1 says that whatever element of the field you take, little c here, okay, and whatever two vectors you take, v, oops, I almost called it v1, but that notation will just get confusing. So we'll take v, oops, I put a bar there, we'll do it the other way around then, v bar and v that you take from fn. Okay, so these are just two vectors. I've just put it in the unconventional order of v bar v rather than v bar, but never mind. Okay, so take two vectors from your set fn, okay, and we want to prove that if we take c scalar multiplied by the addition of v plus v bar, okay, so we've added these two vectors together, that it's the same as if you firstly scalar multiply each of them and then add them in the vector space afterwards. Okay, so this is distributivity, the first distributive law. Okay, so again we'll just apply the definition here. So firstly let's take this left hand side here, so we'll have v plus v bar, and the answer to that of course will be, we'll have x1 plus x1 bar, where this addition is done in the field. Then we'll have x2 plus x2 bar, where this addition is done in the field, all the way up to xn plus xn bar, where this addition is done in the field. And then what we want to do is scalar multiply this entire thing by this element little c here, okay, which is some element of the field. And of course the answer will then be c times x1 plus x1 bar will be our first component, c times x2 plus x2 bar will be our second component, and then it will go all the way up to c times xn plus xn bar here as our nth component. So that will be our final answer to the right hand side here, so I'll underline that in yellow. Okay, now let's take on the, this is the final answer to the left hand side here. Now let's take on the right hand side and show that the vector that we get if we do the right hand side will be the same as this vector here. So now let's take on the right hand side here. So firstly we will scalar multiply both of these vectors by c. Okay, so cv is going to be cx1, cx2, all the way up to cxn here. Okay, c times v bar, we're then going to add it to c times v bar, which will be c times x1 bar, c times x2 bar, all the way up to c times xn bar. Okay, and then we want to add these two together. So these are these things at the moment, and now we're going to add them together, and the overall answer, shall I try and squeeze it in here, it's going to be cx1 plus cx1 bar as our first component. Then we'll have cx2 plus cx2 bar as our second component, and then it'll go on and on all the way up to the nth component, where we'll have cxn plus cxn bar. Okay, and then it will end there. Now, why are these two things equal to one another? Well, again, it will have to be because all the components are equal to one another. And why are all the components equal to one another? Well, let's just take an example, and the same argument is going to apply for all of them. So let's take this first component here. Why is this thing equal to this thing? Well, because this is just basically the distributive law in the field, okay? Because this is addition in the field, this is multiplication in the field, and of course we know that multiplication in the field distributes over addition, so we can rewrite this as exactly this. Okay, so indeed all the components here do match up. These two vectors are equal to one another. Okay, so almost there now, just one last little point to prove, which is part 2 of axiom number 4, the other distributivity, which involves two elements of the field rather than two vectors this time. Okay, so for all c1 and c2, which are elements of the field, and I'll just move this up a little bit, so pick two elements of the field that you like, and pick one element of the vector space. So for all little v is an element of capital V. Okay, so pick whichever elements you like. It needs to be the case that c1 plus c2, where they're added together in the field here, scalar multiplied by the vector must equal c1 scalar multiplied by v plus c2 scalar multiplied by v. Okay, so the scalar multiple of v by c2, and this addition here is addition in the vector space rather than addition in the field, of course, because we're adding two vectors. Okay, so again we're just going to apply the definition to prove this, and we don't really have space, but I suppose I'll try and squeeze it in. Okay, so on this side, firstly, what we're going to do is we're going to take the answer to c1 plus c2 here, and we're going to multiply it by our vector x1, x2, all the way up to xn here. Okay, and what's the answer then that we're going to get? Well, the answer we'll get will look like this. It'll be c1 plus c2 times x1, then we'll have c1 plus c2 times x2, and then it'll go all the way up to, we have c1 plus c2 times xn. Okay, and that will be our answer. Okay, now note, we can use the right distributive law here to expand those in the field, and that's exactly why it's going to equal this side. Okay, so I didn't make a huge point of this when we were doing field theory in the definition of a field video, But the fact that we have this being true in a field, A times B plus C is equal to A times B plus A times C, okay, this is what's known as left distributivity. You can also have it the other way around. B plus C times A is equal to B times A plus C times A. Okay, and if this is true, it follows that this is true also in a field because of commutativity. Okay, so because of commutativity, you can just swap this one around with the A. So you can swap multiplication around, okay, because multiplication is commutative in a field, and turn this one hence into this one. Okay, and then what you can do, or rather you can turn this one into this one, you can then expand it, and then you can swap these back around. So you can take the B and the A, swap those around, take it into BA, and then swap the C and the A around to turn it into CA. Okay, so the instant that left distributivity here, when the multiplication is on the left of the addition, okay, the fact that that is true and commutativity is true implies that right distributivity is also true when the thing that you're multiplying is on the right. Okay, so you can expand all of these basically using right distributivity, and that's actually going to turn it into what this thing is. So let's go over the page and consider what C1 times V plus C2 times V is. Okay, so we're going to consider what is C1 times V plus C2 times V. Okay, right, so let's just apply the definition to this. So C1 times V will be the vector of the form C1 x1, C1 x2, and then it will go all the way up to C1 xn. Okay, so this thing here is exactly this thing here. Okay, and then we want to add it to C2 times V, which will be of the form C2 x1, C2 x2, all the way up to C2 xn, like so. Okay, so this thing here will be equal to this thing here. So now all we have to do is add those together. Okay, and of course we do this component wise, so we'll end up with C1 x1 plus C2 x1, and then we'll end up with C1 x2 plus C2 x2 as our second component, and then it will continue on all the way up to C1 xn plus C2 xn as our nth component. So this will then be the answer, and this is exactly what you would get if you took that other thing and expanded it using right distributivity in the field. Okay, so if you expanded this thing, you would get this thing. So indeed those two vectors are the same, and this part 2 of axiom number 4, distributivity, is satisfied. Okay, so what we've seen now is that this set of all n tuples of elements of the field, Fn, we can equip it with a very natural addition law which is done component wise, and we can equip it with a very natural scalar multiplication which is again done component wise, and that will always form a vector space. Okay, now to complete this discussion then, what I would like to say is just a little bit about the intuitive one, about R3, okay? And you could also apply these arguments to R2, but R2 is obviously just contained in R3. It's part of it, so R3 will do, that's the biggest one after all, that's easily visualizable. So I'd just like to say a little bit about R3. So what we've done here is we've done exactly this, but using the field of real numbers. Okay, so formally what we've done here is just construct 3 tuples of elements of real numbers, so x1, x2, x3, so triples of real numbers where all of these xi are elements of the real numbers. Okay, and formally all we've done is create this massive great set of symbols, put an addition law and a scalar multiplication law on that, okay, and created a vector space, a 3-dimensional real vector space. However, there is something amazing about this vector space, which is that we have a nice intuitive way of visualizing it, and this is the reason that I want to bring it up now, okay, because often when we actually prove these theorems that apply for these abstract vector spaces over these abstract fields, we will go to R3 to get some intuition as to why the theorem is true and what it actually means. And the reason we'll go to R3 is that we have very nice intuition as to what this actually means. Okay, we have an intuitive way of visualizing it. Okay, so I just want to discuss that because we will make use of it in upcoming videos. So the intuitive way that you can view this vector space is that you can view each one of these as being an arrow basically in three-dimensional space. Okay, so if I try and draw a three-dimensional grid here, basically what you're going to view each of these vectors as is a position vector, okay, where the x-coordinate is x1, the y-coordinate is x2, and the z-coordinate is x3. So you'll take x1 here, you'll take x2 here, and let's say x3 is here, and you'll get some arrow like this going to that point in the three-dimensional grid. And then that's our way of visualizing what each vector in this great big set actually is. So we now have a picture to associate with each of the vectors. Okay, and this is intuitively the way that people often visualize vectors, even though, as we've seen, the abstract definition of a vector has nothing to do with this picture, basically. Okay, now, why is this so wonderful? Well, what's so wonderful about this is not only does it give us a picture for each vector, but it also gives us a picture of what it means to add two vectors together and scalar multiply two vectors, or scalar multiply a vector. Okay, so if I've got another vector here, so let's say here is another vector, and I'll have this other vector in turquoise, and I want to add these two vectors together, the way that it actually turns out, that what it means in this pictorial sense, is you put this vector at the end of the other one, like so, and then you take the net thing here. Okay, so you join the end of this green one to the end of the turquoise one. So I'll put the turquoise one here, and that overall vector that you get, the net vector here in orange, that then is your overall answer. So there is this beautiful interpretation of what addition of two vectors means in terms of this picture. In addition, there's a beautiful interpretation as to what scalar multiplication of a vector by some real number actually means. That just sort of scales the vector up. So for instance, if you multiply it by 2, that will double the length of the vector. Okay, so that's wonderful because it gives us an intuitive way of viewing what otherwise is a very abstract mathematical structure. It gives us a picture that we have intuition for, and our brains are very good at understanding pictures, whereas they're not that good at understanding infinite sets of symbols with abstract composition laws defined on them. Okay, so that's the wonderful thing about this. But be aware that what this really is the abstract thing. It's just a set of symbols with the addition law and the scalar multiplication law defined on it. Yes, it's wonderful that we can associate each one of the symbols with this picture here, okay, with an arrow in this picture, and that the addition is then associated with this intuitive joining together of the two vectors, and scalar multiplication is associated with scaling the vector up or down in some cases. Okay, but it's an association basically. This is what it is. It's not identically equal to this. Okay, you can use this picture to gain intuition about this, but fundamentally all this is a set of symbols with an addition law and a scalar multiplication law defined on it. So what I'm saying is don't lose sight of the fact that this is just an abstract mathematical structure. Yes, it has an intuitive physical meaning that you can associate with the abstract mathematical structure, but don't start thinking of these as being the same thing. This is a beautiful intuitive picture. This is an abstract mathematical structure. The fact that this one somehow captures part of this is incredible and gives us intuition about this abstract one, but this is what it is. It's an abstract mathematical object. Okay, so in particular there are lots of things about this picture that are not described at any point in this mathematical structure. For instance, we haven't described anything about what the length of a vector is in this abstract mathematical structure, but this picture has that sort of ingrained into it. We all intuitively in this picture know what the length of one of these arrows is. Okay, so what you have to do is kind of view this as something that we can associate with the abstract mathematical structures in this, but it's not one and the same, basically. So that's my warning. We will use this to understand this, but this is what it is, and it's not identically equal to this. Okay, we're just going to use this to gain intuition about this. Okay, and with that we will end this video on the definition of a vector space.